Okay, let's get started here. Last day of regular class. We're going to finish up parallel processing, and we will review for the final. Of course, the final is Tuesday finals week at 1 p.m. Are there any questions before we get started here? Okay, before we actually get going, I would like to mention that I have posted all of your grades so far this semester on the Blackboard website for our course. And the reason why I did that is because, of course, I can make recording errors. I just want to make sure that what I've recorded is what you guys actually have for your grade. It also serves as a good way to remind you of how grades are calculated with respect to what's stated on the syllabus. So let's say for a particular student, day number 1 quiz, they got 10 points out of 10 points. Project number 1, 65 out of 70 points. If you put all this together and find the proportion of points, then this ends up being 96.18. So 30% of your grade, or this student's grade, would be 96.18. Let's say test 1 was a 95, test 2 was an 85. The average of those, that's 90%. This ends up meaning that 50% of your grade will be this 90%. On Blackboard, I have actually put what is your current course grade. And this is found from taking 0.3 times this project's grade plus 0.5 times the test grade and divide all that by 0.8 because we've had 80% of our entire grade so far. So this would translate it to 92.3. Then, after you guys take the final exam, after I get everything graded, I will post a message to the listserv saying, hey, everything is graded. You can go to the Blackboard website to actually see what you got on the test and also your final grade. So if a student got a final exam grade of 89%, the course grade then would be 0.3 times this, 0.5 times this, plus then 0.2 times the 89 translates into 91.65, which is an A minus. So directly from what the syllabus says, sometimes students get a little bit confused because I assign a percentage grade to every main part of the course, but that's how it's calculated. Are there any questions? Okay, good. Let's finish up parallel processing. Okay, so last time we talked about the parallel package. Today we're going to talk about the for each package. This was actually the first package that I tried to use for parallel processing about 2 years ago. I was partially successful, but not totally successful with it. But then over fall break, when I looked into this some more, I figured out fully how to use it. This package was developed by Revolution Analytics. I think we talked about that company here in class. Again, they make their own version of R and then sell it to people and companies. And they've written some of their own packages as well. One of the things that they're really into is big data. And this is probably why they did the parallel processing stuff, so that you can analyze big data sets simultaneously or on multiple core processors at the same time. There is a nice vignette on the package available there. And the for each package, or the for each function of the for each package, is written in a way to take advantage of what you're used to already in terms of the for function. So this is how for each works. For each, then you're going to iterate over I equal 1 to n. I'm sorry, I equal 1 to r. So you're going to have, let's say, repeat something r times. And then in the end, when you've done it r times, you are going to combine them by using a particular function, like maybe the C function. So if your end result for the for each package, for the for each function, is to produce a vector of information in the end, and maybe your statistic that you're calculating r times, it's going to combine it, if I use the C function, it's going to combine it into a vector. If instead I use a cbind function, it's going to combine it over the multiple core processors that are being used, or multiple cores, I should say, of the processor. It's going to combine them by column. So let's say column 1 would be core 1, column 2 would be core 2, and so on in terms of the results. You could also use the list function as well to combine it in terms of a list. So notice the argument here is called dot combine. And then you say %do par, which is like for do this, and then put in your code that you want executed on each form. Okay? So it's fairly simple. I think a little bit easier, the structure is a little bit easier than with the parallel package. One advantage that this function has is that if you remember with the parallel package, we had to write a function that would be run on each core, and we had to actually include all the code, like even reading in the data set. The nice thing about the for each function is that you can read in the data set, let's say, above it in your program, and then call whatever data frame or whatever you're reading in is, call it right in here. So that's a little bit nice. But still, what ends up happening is when you use this function, basically multiple R sessions are open. And because of that, if there are any additional packages that are not automatically loaded in R, at the very beginning of using R, you're going to have to load the packages again. So like, for example, you'll see with the boot package, I have to actually load that inside the for each code. The Revolution Analytics also has a package called do parallel, which basically sets up, your core process to do what you need to do. So let's take a look at an example. The AC data once again, and I decided how could I use, let's say, the for function without just the plain old for function, without using the boot function at all. And then we'll compare for to for each to see how the codes would be similar or different. So here's my AC data. I'm going to repeat it 1,000 times, start the clock. I'm going to save my results into something called save.res1. So it's just going to have a vector of results. And then use the for function. So for I in 1 to R, repeat the following. Take a sample of my indices of my data. So 1 to n, and I think the n is 12 in this case. Take a sample with replacement, then return the mean, where I only use those corresponding data elements with these corresponding indices that we're resetting. Okay? Put it in save.res. If you want to, you could calculate the variance and then record the time to 0.0028 minutes, not much. Is everyone clear about this use of the for? Okay. Now let's do this with the for each function. So the first thing I need to do is say, okay, let's use the function. I'm surprised I didn't do this. Wait. We need to say library for each. I don't remember off the top of my head, but if by doing library do parallel, it might automatically load for each for you. You can experiment on your own. It's not that big of a deal. Then similar to what we've done before, I say make cluster, and note that this is actually coming from the parallel package though itself. And I specify 2 clusters. And then register do parallel. This comes from the do parallel package. Register the clusters. It's just the way to do it. Okay? Syntax is sometimes a little odd, but that's not good. Then I start the clock again with proc.time. I get my my streams of random numbers, essentially. 2 different streams because I had two cores that I'm using. And then we get to for each. I'm going to save the results into something called save.res2. Notice I don't need to initialize it at all like I did with save.res1. For each I equal 1 to R, I'm going to combine the results by the C function. And then I have essentially the same code as what we had previously with the for function. But the key is, again, this is going to be going over 2 different two different cores at the same time. Here's my variance, a little bit different from before, but again, we're using different random numbers. Remember this, that set.c is not going to give you the same thing as the C cluster set RNG string will.
Quick question.
Yeah.
So your I is 1 to R. That's your total number of resamples, right?
Yep.
It splits them up
It splits it itself.
Okay.
So that's the cool thing. So here's the number of minutes it took to run. 2.5, which is a lot more than what we did with the for loop. And here I'm using 2 cores. Before with the for loop I was just using 1. So what's going on here? Well, I looked into it, and others have had the same problem. And supposedly there's a lot of time spent with the combination of the results at the end. This is what's causing the problem. I don't know. I think there might be some other reasons too. I'm not going to get into them here. But this is just to give you a caution here that even though the for each function is set up really nice, you don't necessarily run it exactly like you do with the for function. So instead what I decided to do was look at, well, maybe I could rewrite my code here in a similar manner to what we did with the parallel function. What would happen? Would I get time savings? So I get the cores ready to go. I write a calc.t function, like what we've done in the past. I set my seed number, and then I save the results in save.res3 from for each. And notice what I say here. I equal 1:2. What I'm going to do is, again, use 2 cores, but I'm going to allow, I'm going to use 2 cores and basically do half my resamples on one, half on the other. And so I'm kind of splitting it up on my own by saying, okay, let's now inside here do the boot function. Notice the number of resamples are divided by 2. So this is like what we did with the parallel package. And then I return in the end boot.per $t. Remember, this is going to just be a vector of my t stars. And look how I combine them in the end with the C function. And also notice I use the .packages argument and say boot to say, okay, load up the boot package. So I run everything, and look what I get, 0.006. So how you write your code matters. This is still not as fast as the for function itself, but it's pretty close. So what I decided to do was do some benchmarking, where let's crank up the number of resamples and see what happens, to see if I do get a time savings. And we can see at 1 million resamples, which is what we had with the parallel package example. Here's my for function, 0.45 minutes for each, 2 cores, 0.2278, which is very similar to what we had with the parallel package. Okay. Any questions? So the next stuff here talks about the Holland Computing Center and their supercomputers there. I'm not going to go through it in detail in this class. But I encourage you, or I shouldn't say encourage, I want you to read it. Because the stuff here can be beneficial to your research. Again, as I mentioned before, the next time I have a large simulation study to run, I'll probably use those computers versus trying to use computers in our department. But some comments I do want to make, though. It's not necessarily easy using their computers. Their computers run on a Unix operating system without any kind of Windows at all. It's all text-based Unix. So you have to know the right commands. Fortunately, when I was in grad school, we had a large number of Unix workstations, and so I'm familiar with the language in terms of the correct syntax and the correct words to use. So it didn't take me too long to pick it up. But obviously, if you don't have any Unix experience, it might take you a little bit. But what I try to do in this next 10 pages is to give you the important commands to know. Let's see. It's like going back in time when I was on Tusker, one of their supercomputers over there. I hadn't used some of my knowledge of Unix for about 10 years. I was like, oh yeah, that's right. Anyway, I mean, for the most advanced computing, people use Unix. So that's why that's being used over there. Let's see. I did do some benchmarking. So on page 29, I ran basically the same kind of code that we had before, where I went up to 25 cores that I was using. And I did 4 different runs because, of course, you should have variability from one run to the next. And since I'm a statistician, I know that, so that's why I decided to do 4 runs this time. I did 4 runs up until when I was using 10 cores. And you can see over in, you have 4 different color lines here. You can see for the 4 runs how the time goes down until you get to about 5 cores, and then things are not going to, you're not going to have much more benefit from after that. But I did take one of my runs up to 25 cores, and even though you do see this down here, I bet that's probably just due to the simulation variability. On page 30, the boot function actually now does have a new argument in it called parallel. But you can only use this with the Unix operating system. So that's why we went through the trouble of talking about Windows and how to do that stuff. Really, I don't think it would be too difficult to extend the code to Windows. I think someone could do it. Note that for parallel, the argument, it allows you to use 2 different possible packages for the parallel process, multi-core and SNO. If you remember last time I mentioned how basically the parallel package itself was built upon previous work that was done with multi-core and SNO. So I decided, okay, now that we have this parallel package, I wouldn't be surprised if the people who control the boot package, if they will allow you to have a parallel equal parallel argument value there in the future. So right now I'm not going to worry about how to use the boot package or how to use the boot function on Unix operating systems with this parallel argument. There's something also that you could do for parallel processing called grid computing. If you ever wanted to, well, grid computing basically is a way that you could use computers all over the world. Not just the computers here at UNL. You basically submit your program to this, let's say, central unit, and it will then find some open computer around the world and run it for you. So if you have very, very large jobs, that's a way to do it. One last comment. I might have mentioned this before, but I think it's good to say it again if I did. If you want to use your computer simultaneously while you're doing parallel processing, do not use all the cores at the same time. So let's say if I have a 4-core machine, I would not set up my parallel processing to use all 4 cores at the same time if I wanted to do some other kind of computing in my machine. Because if you were using all the cores and you tried to do some other stuff, your computer's too busy already. It's not going to be able to do anything. So when I have tried parallel processing, or even in simulation studies without parallel processing, I always leave at least 1 core open so I can do other stuff. Okay? So that concludes the parallel processing section. There is one question on the final exam from this section, but it is the extra credit question. Okay? So, if you don't want to look at this anymore, you don't have to, but you're going to be missing on extra credit. Any questions?
Is there any way, if we have like a single analysis, it's going to take a really long time, so it's not something, the same thing, doing over and over again. How do you go about speeding that up?
So, perhaps you are fitting some kind of model that, let's say, takes like an hour to fit maybe because we have some high-dimensional integration maybe, or
Yeah, something like that.
that is, that's no longer in the embarrassingly parallel setting.
Yeah.
Can you do it with parallel processing? Depends upon the problem. The key is in that kind of setting, you might have to communicate. Let's say when you're dealing with something, when you're doing some kind of fitting over here, you might have to communicate with some kind of fitting over here at the same time. And can that be done? It depends. For example, I attended a session on the EM algorithm at the last JSM. Do you know what EM algorithm? Basically, it's just a nice little algorithm that people use. For those of you who do not know it, it's a nice little algorithm that people use to fit models in certain situations. With the EM algorithm, what this person needed to do was, I think you might have maybe 100 or 1,000 different things that needed to go through the E and the M cycle. And so what they were doing was they were setting up the parallel processing so that, let's say, 100 of the things that needed to go through the EM cycle go on this core, 100 go on this core. And the research then was, do I still get the, let's say, the convergence of the parameter estimates to the right place? At least for their research, it did, even though things were being done separately. And so I think that's an area of research that's open to figure that out, to do that kind of stuff. I guess for those of you, a couple of you took my categorical class last semester, or last semester. I cannot remember what the function's called, but if you remember when we were doing profile likelihood ratio intervals, there was a function that we were using that allowed an actual argument called multi.core, I believe. And it allowed, if you just put multi.core equal 2, you use 2 cores. Now, in that kind of setting, when you do profile likelihood ratio intervals, just think of them in general, for those of you who weren't in my class, the communication that needs to be done, I don't think it can be totally embarrassingly parallel. And so somehow they figured out, I don't know how, I haven't looked into it in detail, but somehow they figured out how to do that.
Have you done any parallel processing in SAS?
I have not, but one of the first times that I've heard of parallel processing used was, I can't think of the guy's name, he's at Texas Tech. He does a lot of multi-comparison stuff. And he was using parallel processing to do that. Somehow he was doing it in SAS at the time. I don't know if he's still using SAS, though. That was like in 2000. Any other questions? Okay, let's talk about the final exam. So, virtual office hours. Monday night, 9 to 10 p.m. So if you have any last-minute questions, please feel free to stop by the chat room. The general layout for the test itself, there's 100 points possible. About 20 points deal with derivations. So you might have to find the expected value of T star, whatever T's represent. You might have to show how a confidence interval comes about. Approximately 30 points is let's say, data analysis, where you're going to have to use R to do stuff. So I'm going to give you a data set. You do some stuff with R. Then approximately 50 points are my, I don't know, maybe they're famous, but I like to think of them as my famous short answer questions, where they're not necessarily interconnected in any way. Are they famous in the department?
I was going to say infamous.
I really like the questions because it helps me narrow down, do you understand a particular topic?
So does additional question, that complaint question, fall in that 50?
Thank you. Sorry, I forgot about that. 40. So you can kind of think of the last one, the 10 points is a short answer question, then which would be the take home. Again, please email that to me before the exam. In total, about 50% of the test deals with Chapter 6. And again, you might be thinking, well, geez, that's a lot of weight for a comprehensive exam, but you haven't been actually tested at all on Chapter 6 yet. And if you actually go through the math, you'll see that Chapter 6 is actually a smaller portion of your overall grade than the other chapters. And of course, there's the 2 points. I gave that away. It's not worth much, but there's 2 points extra credit. It's not a difficult question, but it deals with something that's in any of those 32 pages. There is no, you don't have to use R to do it. Okay? No, are my extra credit questions famous? I used to have some students who were always trying to guess what the extra credit would be, and then they would get disappointed when I decided to have them do something totally different.
We were really close from the second exam while we were guessing.
I forget what was the
When
question.
were you hired?
Oh, yeah.
We were looking at when was that the K-State guy tackled and stuff like that, and so we knew it was from that presentation.
So with the exam, there's the formula sheet, the notation sheet. I'll pass that out. Again, you can download it from the test web page to see what it will look like. The format of the exam, as you can tell, it's very similar to what we've had before. Again, once the tests are graded, I will post something to the listserv saying the tests are graded. You should go to Blackboard to take a look at your final exam grade and your final overall course grade. If you would like to see your final exam, though, please make an appointment to come see me. Okay? You can try stopping by my office, but I can't guarantee that I will be there, especially since we are interviewing people for our department head position. So I'm going to be away from my office a lot for the interviewing stuff. Okay, so that's the format of the test. Let's do some review. I'm just going to do Chapter 6 because I would basically say exactly the same thing for Chapters 2 through 5. And since these reviews are recorded, we'll go back and view the video. So we talked about, again, 2 different ways to do the resampling with respect to regression models. One was model-based resampling. Make sure you understand the motivation behind why someone would want to do that. But also, there's some additional assumptions that come along with doing resampling like this as well. We talked about expected values, how to derive expected values with respect to the beta hats. And what do we actually resample? Well, we resample these mean, adjusted, modified residuals. Well, why do we resample those versus maybe just the residuals themselves? Why do we mean adjust them? That might be good. Short answer question. Obviously, make sure you know how to implement it. We also talked about case-based resampling. What's the motivation behind doing something like this? Well, it just kind of follows from what we've been doing in terms of going back to Chapter 2. Make sure you know how to actually implement case-based resampling. And I think the toughest part of this chapter was dealing with hypothesis testing. How can I test, is beta 1 equal to 0 or not? Since we need to resample under the null hypothesis, we have to adjust how we do this model-based resampling. We have to adjust how we do the case-based resampling. It's not necessarily, once you see it, it makes sense, but it's not necessarily straightforward always how to go about doing that. And we also talked about, of course, hypothesis tests for, like, let's say, beta equal 1 versus beta not equal 1. Make sure you understand how to do that. And then we concluded the chapter by talking about prediction intervals. With these prediction intervals, we're no longer trying to capture a constant value inside a confidence interval. Now we're trying to capture a random variable. So there's this additional variability that you have to account for. And the way that we did that by taking an extra element, in our resample. And make sure that you are familiar with how to, do various extensions, like that we didn't necessarily do exactly in class. How to find a confidence interval for beta 1. How to do confidence interval for the expected value of y. How to do a confidence interval for x if you're doing inverse prediction. We didn't go over those because it's just basically applying what we already did. But now all we have is a different statistic that we're going to work with. Yeah. I think I'm pretty much done.
So for those, for like the basic confidence interval, you don't need to estimate sort of associate variance term for each replication, but for like student size we would. So obviously we know what it would be for beta and expected value of y and so forth, but for like x.
I would give it to you.
Okay.
I would show you how to do it.
Okay.
Because obviously if you haven't taken STAT 870, at least with me, you wouldn't necessarily know how to do that exactly with R. But I would give you some background. Okay, so that's all I had specifically then for review, since it's just basically Chapter 6. Do you guys have any questions?
We looked. Sorry. I looked at the Chapter 6 homework, and they were. One was kind of a derivation type question, and the other was some sort of short answer. There wasn't a particular kind of practice to implement any of this. Is there a problem or two that you could recommend?
I would recommend taking a look at the book.
Okay.
Try to
So do they have like their practicals or just replicate their examples?
You could try their practicals. You could try to replicate those examples. Remember with the practicals, the codes they're given to you.
Right.
So you could just try to implement that.
Okay.
I think that would be good practice.
Okay.
In the Chapter 6 notes, for the beginning, you're deriving some sort of variance term. And I'm just wondering about one particular spot. So it's
Probably this one. Oh, sorry. It's kind of hard to see.
no, it's maybe later on when you're showing that it's almost equal to sigma squared. Basically, you have like variance plus variance minus the covariance term. Now, I was wondering why it wasn't 2 times covariance. So right there.
Okay.
Maybe I have my formulas a lot.
So you're saying a 2
Yeah.
right there? Let's do the basic principles. So let's say A and B are constants, X and Y are random variables. Does everyone agree? Is that a yes or no? It's not going to change the meaning. But, yeah. Also, it was pointed out to me before class too that this should have been a negative there. This should have been a negative. This should have been a negative. Again, it doesn't change the meaning. Sorry about that. I think of all my classes, you guys have been the best with catching my errors. Which is good because I want to make sure my stuff is right. I am disappointed at myself.
You type enough formulas and you're bound to lose a minus in some case.
Any other questions? Okay then. Thank you very much for taking the course. Kind of as I guess as a thank you for being a good class and catching all my errors. I would like to take all of you out for ice cream over at the dairy store if you are interested in buying. I know this is a busy time of the semester, so if you'd rather go back to your office or go home and get some work done, you're not going to hurt my feelings. But if you'd like to come with me to the dairy store, I'm buying. So that's it for today. And I guess if you're watching on video right now, you need to go get ice cream there or wherever you're at.